For our next problem, the position of an object at time t is given by the following function. So s of t equals the square root of 3t plus 4, where t is greater than or equal to 0 and is in seconds, and s is going to be measured in meters. So the first part says, well, let's use the definition of the derivative to determine the velocity of the object at time t. So the velocity, v of t, is going to equal the derivative of the position function. So we're going to have to use the definition of the derivative in order to compute that. So the first thing that I'm going to do is I'm going to find s of t plus h. So that's going to be 3 times t plus h plus 4, all under a square root. And this is going to give me 3t plus 3h plus 4 under our square root. S of t is going to be our original function. So now if I want to set up my difference quotient says, well, it's going to be s of t plus h minus s of t all over h. So the first thing I'm going to do is put in my first function I found. So hopefully with these colors you can kind of see where all the pieces are now. So s of t plus h minus s of t all over h. And I want to simplify this until that original h in the denominator goes away. So I don't have anything to factor. I don't have any handy little tricks, right? And I have 2 radicals in the numerator. So one of the things we could do, and we saw this in the advice section, is we can try what we call the conjugate. So the conjugate is when you multiply something by the exact same expression, but you change the sign, right? So there are some plus signs underneath the radical, but that's not what we mean. We're saying I have one term minus the other term. So I'm going to multiply it by that exact same term, 3t plus 3h plus 4 under a square root, and I'm going to now add it to the square root of 3t plus 4. So in order to make this legal in math, right, whatever you do to the numerator, we have to do the same thing to the denominator. And the reason the conjugate works is basically what we're saying is we have an a minus a b, right, times an a plus a b. So we actually have created a difference of squares. And that's going to multiply out to be the first term squared minus the second term squared. And that comes in real handy with radicals because it's sort of a way of squaring both radicals at the same time. So the first term, when I multiply these 2 terms together, I get 3t plus 3h plus 4, but now my radical's gone, minus this term times this term, which is just 3t plus 4. And this is going to be all over the denominator. So we didn't do anything with this stuff. So this just rides on over. So we have h times all of this. So we only lose the radicals in the numerator. The ones in the denominator are just still along for the ride. Now I can try to simplify this numerator. So in the numerator, I see I have a 3t minus a 3t. So these t's, 3t's cancel. I have a 4 minus a 4. So these 4's cancel. And now what I'm left with is 3h over h times 3t plus 3h plus 4, still under a radical, plus 3t plus 4 under a square root. And my h's cancel. So remember, as soon as that original h in the denominator is canceled, I'm ready to evaluate the limit. So I like to simplify the difference quotient and then do the limit so I don't have to write limit, 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 limit through every algebra step. So s prime of t, which is going to be our function v of t, is going to be the limit as h approaches 0 of 3 over the square root of 3t plus 3h plus 4 plus the square root of 3t plus 4. So now I can plug in a 0 everywhere I see an h. And when I zero out this term, I'm basically going to have the square root of 3t plus 4 plus the square root of 3t plus 4. So that means this limit will be 3 over 2 times the square root of 3t plus 4. So this is our velocity function. Part B says we'll determine all the values of t at which s is differentiable. So some of you might, and not a crazy idea, might go back and you might look at the equation and just say, oh, well, I just need to check where this isn't a negative because you can have negatives under the radical, and I also need to make sure that this isn't going to be 0. So let's go back though and make sure that we check the domain of s of t, because anywhere that s of t didn't exist, its derivative function can't exist either. So sometimes when you take a derivative, the equation might look like it will accept values that the original function would not accept, and you might include things in your domain that you actually can't do. So if we go back and look at this function, the domain of this function is 0 to infinity. And that's because I was told here that t cannot be less than 0. So it actually says here t can equal 0. So the domain of our position function, oops, let's use a colon here, not an equal sign, is 0 included to infinity. But let's look at our derivative function. So now the derivative function, that same radical pops back up, but now it's in the denominator. So let's double check that this isn't going to work. So in a kind of conventional pre-calc class and just in general, if you only looked at the function, you might say, well, 3t plus 4 has to be greater than 0 because it's got to be positive, and it also cannot equal 0 because it would have a 0 in the denominator. So if I solve this inequality, I would actually see that t must be greater than -4/3. So I can tell you right now, a very common wrong answer on this question would be -4/3 not included to infinity. And that would be wrong because the original function said time cannot be less than 0. So if it can't be less than 0 in the position function, it can't be less than 0 in its derivative function. So time, right, cannot be negative. So that means that if anything less than -4/3 is the only thing that's going to put us in trouble here, then that means the domain of v of t is also 0 to positive infinity. Now, the question is, do I actually include that 0 or not? So in order for a function to be differentiable, if we look at this domain, right, I would have to make sure that that limit exists at 0. Excuse me, I'm so sorry, just sneezed. We would have to make sure that the limit would exist at 0. And we actually learned earlier in limits that we cannot include 0 here. Oops. So s prime of 0 would actually not exist because we can't differentiate on the edge of our domain. So we would actually not include that 0. So you can't take the derivative or use the definition of the derivative at 0 here because you could only come at it from one side. There's nothing going on to the left of that value. So we wouldn't actually take the derivative at 0. We could take it everywhere to the right of 0. C says determine the velocity of the object when t is 1 second. Well, since we now have a handy formula for v of t, we just simply now evaluate v of 1. So v of 1 is going to be 3 divided by 2 times the square root of 3 times 1 plus 4. And that equals 3 over 2 root 7. And the units are going to be meters per second. Part D says, well, let's find the equation of a tangent line on the graph when t is 1 second. So we know that our value of our point is 1. We need to plug that point into our function, and when we plug this into the original function, we get the square root of 7. We just found in our previous part that the derivative at 1 is 3 over 2 root 7. So that is our slope. So now we just pop this information into the point slope formula. So y minus the square root of 7 will equal 3 over 2 root 7 times x minus 1. And this is the equation of our tangent line.